Hello everybody, it's me, Blacklemori. I'm going to walk you through how to use these Python notebooks to, well, I'm only going to cover the SDF one because I am tired. So first thing what you're going to want to do is download it from the Google Drive page and it'll zip it up. Okay, great. So it's downloaded. So I'm going to open it up and extract it to, downloads, my downloads folder. So it goes there. So now I've opened it up in my downloads folder. And what you're going to want to do is you're going to want to open a terminal. So I'm using Linux. I don't know how to do this on Windows. And you want to install this program called Jupyter. So it's like GUI, Jupyter, yeah. So you get this program. I think you do like, you can install it using pip3. So here I'm going pip3 install Jupyter Lab. And then now you can run Jupyter Notebook from this directory. And it'll start up a browser. So I'm just going to close this browser. And you can copy and paste one of these links to the browser. You open that up. And now you are basically able to open any of these notebooks. So we're going to open up the SDF notebook. So this is, actually I'm going to go directly to this page. So this notebook is based off of the Collab Notebook from the original SirenNet paper. So if you go to the Collab Notebook, this opens with Google Colab, so you could do some experiments there, but this is specifically, this old notebook that was released with the paper only does a couple of things. Namely, it fits an image to, it fits a very large SirenNet to an image. And then later it fits the gradient of the image. So like the derivative of the image it fits. So that's the stuff down here. So I modified this stuff to do 3 things. One was fitting a color image, fitting a color light field. So a light field is, well, I'm not going to get into light fields right now. And then I think what everyone's here for is the SDF fitting. Hold on, I'm going to explain what a SirenNet is real quick. I'm all over the place today, whatever, I'm not going to edit this video. Okay, so SirenNet is just a neural network. So a neural network, it's got like input nodes. Actually, I want to use the pen tool. There you go. It's a bunch of input nodes, and then there's hidden layers. So these are the hidden layers. And then this is the output. So normally, well, it depends on the network, but for this one, there's only one output, and it's the distance to the surface of the model. So it's the actual SDF output. And the input, there's actually only 3 of them. I should delete one of these. There's 3 of them, and it's the X, Y, and Z component. Select none. X, Y, and Z. Oh, that's not a Z, that's an X, a Z. So for a neural network, all the layers are connected like completely. So all the Z is connected here, the X is connected over here, and the Y's are connected over here. And what these connection means is basically each of these are variables, essentially. And this variable, it's a weighted sum of all the inputs. This variable is a different weighted sum of all the inputs, and this one's a different weighted sum of all the inputs. And then once you get that sum, you pass it through this nonlinearity, which is basically just a function. For a lot of networks, it's a ReLU, which is just a, it's basically like max of 0 in the number. So it is essentially like cut off all negative numbers, and that's the nonlinearity. But for SirenNet, the nonlinearity is just the sign function. Oh, I forgot one thing. There's a bias term. A bias term is just the constant value 1, so you can like offset the inputs a little bit. So that also goes in. You don't have to worry about that too much, but if you are really interested in this kind of thing, that's the basics. And then the hidden layer goes to another hidden layer, which is like this. And basically the same thing, and this goes through a sign. And then these layers all get added up with another weighted sum to get the actual output. So that's the gist of it. However, I did make a major, no, not major, but I did make a modification to the architecture because these SirenNets seem to like to be wide, meaning there's like a lot of nodes in the HID layers. So like a hidden layer might be like 512 units wide, but the actual height of the network, meaning the number of layers, is only like 4. So in the original paper, they had like a 512 by 4 network trained on an image. However, 512 by 512, that's the matrix you need to do this per layer multiply. Those are huge, and so I wanted to see if I can make it where the network is tall instead of wide. So what I did was I added these skip connections. And let me see if I can describe this. So instead of the network just passing the values up through here, once they finish, the values are added to the previous layer. So this is added, this is added, and this is added. And then that's the actual output. So this is a horrible drawing. So what the skip connections are intended to do, it's kind of like the ResNet, if you've heard of ResNet, it's residual networks, where basically each layer only has to figure out something to add to make the output better. So basically, how do I say this? This video is a mess. Anyway, the point is that with these skip connections, the network can be deeper because the gradient information can propagate down better whenever it does its training phase. Anyway, let's go back to the networks. This is a horrible explanation. Okay, so back to the network, the actual Python notebook. So Python notebook is just a bunch of like bits of text with like code in between. And so you're going to need to download, this is just Python code. So you're going to need to download and install Torch, PIL. So basically every import here and then every import later. So there's like, you don't have to install math because that's like a standard library, but mesh to SDF is a thing you install using pip. So you go like pip3 install mesh to SDF, and then that installs that. And you import all that stuff. And so you need Torch, you need PIL, you need Torch Vision, NumPy, skimage, matplotlib. You can probably install all that stuff through pip. For those you can't, it might be in your package manager. So the first thing is just taken directly from the original paper. So you click on the cell and you click run to actually run that code. So what you do is just you go through each one and run it. So I ran this one. This basically defines the SirenNet itself. And my changes are like to add the skip connections are right here. Where is it? It's like if it has a skip connection, you just add the intermediate to the input. And then there's like this multiplication term that I added just because I thought that higher layers would take care of like higher frequency stuff. And so they would have to have less magnitude. Anyway, that's not important. Moving on. And we run SDF fitting, which is just it just generates the data set from the mesh to SDF thing. So it loads the mesh, it generates like a point cloud. The mesh to SDF library has this like function called sample SDF near surface, which uses a mechanism, like basically it samples the SDF like in a unit sphere and then also very close to the surface. However, I found that like the network doesn't like that. It likes a lot of samples on the Unisphere, so I added more Unitsphere samples here. By didn't like that, I mean I see a lot of weird melting artifacts where the network probably overfits in that area. So this is the actual like loading of the object file. So here we got bunny2.object, but we're going to go through the process of actually like creating one of these obj files. So I'm going to delete that. And I'm going to find the, what is it called? It's the Utah teapot object. So I'm going to save that to my downloads. And so I have to open this in Blender because I don't really know how else to edit it. So we're going to open up Blender here. Delete the default cube as always. And we import the object file we just downloaded. So that's in downloads. It's going to be teapot. So you got the teapot here. And so the thing about the object, it has to fit within the unit sphere, which is just a sphere with radius 1. So I'm gonna spawn in a sphere using add. So I add a UV sphere, and it was spawned over there, which is annoying. So I press N. So you press the N key, and you change the location to the origin. And it's already a unit sphere. Its dimensions are 2 meters by 2 meters by 2 meters, which means it has a radius of 1 meter. And so we just have to scale this down so it fits within the sphere. So I scale it down. I'm going to change to viewport shading. I'm going to change the viewport shading to be wireframe so I can see inside. And then I use the G key to move and press the Z key to move it along the Z axis. So I move that down here. This part's kind of sticking out, so I'm going to move it along the Y or X axis. So I press GX, and that moves it across the X axis. And now it fits within the sphere. So we're going to delete the sphere now and export as OBJ. And then this goes into our neural experience, or we call this teapot. Teapot.object. Okay, export. So we go back over here and we change this to teapot. And this step's going to take a long time. I don't know why the mesh to SDF like code is so slow, but this takes a while to load. Okay, it ran, and the output here is just to debug the size of each like object that comes out, so you don't have to worry about that. Next up is this. This is probably going to crash because I forgot to remove the call to it here. So this is the actual code that like puts the that actually like generates the Shadertoy code from the model. So if I run this, and by model I don't mean like the actual 3D model, I mean like the neural network model. It's kind of confusing because like the network, like the trained network is called a model, like the way you'd say a statistical model, but we're also working with like 3D models and they're not the same thing. The way this thing works is it just like splits up the matrix multiplies into mat4 multiplies. So it just manually simulates or manually emulates like a large matrix multiply by doing multiple smaller matrix multiplies. And don't read the code too hard, it's very bad. Okay, so that's been run. This is the actual training code. So basically what this does is it takes in a number of hidden features. So that's the number of like units per layer. So that's this number, so 1, 2, 3. And then the number of hidden layers, which is the actual like depth of the network. So here there's two layers. And one thing to keep in mind is hidden features has to be divisible by 4 so that this code will work. So just multiples of 4, like 4, 8, 12, 16, that kind of thing. Hidden layers can be any number, as long as it's over 1, I think. All right, so, yeah. And then omega, this omega value here. It's sort of like, in the original paper, it's always 30 for math reasons, and I'm not totally sure why. But here, at least with these small models, where it's just like a couple of hidden features and like a bunch of layers, omega is more like a hint to how high frequency the object is. So like, if your object has like a lot of fine detail, you might want to increase omega and it might help, but there's also a chance it'll just cause the model to look melty. So you have to really test it out and try different things. So we're going to run this, and here we've got a 16 hidden unit network with 2 hidden layers, and we're setting omega to 15. So let's try this. So let's run that, and this is going to take a while. If it crashes here and it says like cannot open like CUDA or whatever, that's because this code uses CUDA, which is a what's the word? It's like a GPU accelerated library. And if you don't have CUDA, I think if you just remove all these .CUDA calls, so if you search for .CUDA everywhere and remove it, I think it'll use the CPU. So if you don't have a graphics card, or specifically an NVIDIA graphics card, I think it should still work if you remove .CUDA in a bunch of places. So the .CUDA is here, and then .CUDA is like here and here. And yeah, so it should work once you remove that. It'll just be slower because it's going to be using the CPU. But yeah, this training step's pretty slow depending on how big the network is. Okay, so this is our trained data. Let's see if this worked out. So we're going to copy this, and we're going to go to Shadertoy. And we're going to open up the bunny. I'm going to make this bigger. So you can just replace, so everything after this comment, you can replace with your generated stuff. So I'm going to paste that here. And oh my god, look, it's the thing. It's all fucked up. Look, it's all warped and shit. Okay. So this is sort of to be expected because the network is like, yes, there's a couple things wrong here. So first of all, see how like every number only has 2 significant digits? To change that, I should have fixed this before I uploaded the files, but if you change these numbers from 2 to 3 in the dump data or the print vec4 and mat4 stuff, it'll change the precision of the output. So when I run this, and actually I don't want to train again, so I'm going to copy this and paste it afterwards. This is why this thing was here. It's because I was testing stuff out. But anyway, now there's more precision, and now there's going to be less like floating point errors with the actual network. So when I paste this in here, it's going to be larger because there's more like numbers, but it's probably going to make it look better. So let's run this. Yeah, so that is less glitchy. And it's still like fucked up. Don't get me wrong. Like it's definitely the teapot, but it's like warped and weird. And that's generally, I think, because the teapot is more of a constructed shape than a organic shape. Like the bunny, it works out because like if the bunny is a little bit warped, it kind of makes sense because like it's an organic shape. But here it's like a symmetric object, and then the asymmetries really call out to you. So I have an idea, and we're going to go a little bit off the rails here and start doing some experimentation, so bear with me. And namely, so my thought is, the network needs to learn that the object is symmetric. So what we could maybe do is we can just say, oh, I don't want you to learn the whole object. I just want you to learn like this left side or whatever. And then like I only want you to learn one side of the object. And then I'll manually mirror it. So if I do something like, so let's do something. So if we say like p.x is equal to abs of p.x. I'm going to have to zoom this thing in. So now it's symmetric because I've mirrored it along the x-axis. There is a bit of a seam here. See how there's like a seam on the... Can I like go full screen here? Yeah. So there's a seam on the axis here. And that's because ABS sort of has this hard edge. But you can solve that by doing the square root of p.x times p. This is like smooth ABS, and you add by a little value here. So now that the seam is slightly gone, I think if we increase the value here, it's like even smoother, but it gets rid of like the middle bits. And you can solve that by subtracting by 0.01 here. I think you have to go higher. Yeah, so now it's, well, now it's wider, but you get the idea. You can play with these numbers. Like maybe like 0.5, and then like, I think this number is like the square root of that number. So if I just so square root of this, I should add this to my, anyway. Now it's symmetric, so it's a little bit wider, but whatever. But anyway, so what I'm thinking is maybe we can change the network so it only learns one side of it, and then it will, when we mirror it, it'll just be fine. So let's try that. So what we're going to do is when we generate this code here, what we could do is we could reject all coordinates that are on one side of this mirror plane. So as you can see, the first coordinate is the y coordinate, the second coordinate is the z coordinate, and the next coordinate is the x coordinate, and the x coordinate is the one we want to mirror along. So what we do is we say we only want, so we say like self.coordinates is equal to the coordinates who z coordinate, or x coordinate, which is the second coordinate, because it's 0 indexed, is less than, hold on, yeah, This is some rank ass code right here, but anyway, it's less than 0. And we have to do that for samples as well, and it has to happen before we modify the coordinates thing. So let's see if this works. So I run this, and I run this. This is going to take a while. Oh yeah, I forgot to mention. You can uncomment this stuff, and then it shows you a preview of all the points that have been loaded in like a 3D viewer. I haven't tried this before, so who knows? Who knows what'll happen? All right, so let's run the training step again. Okay. I can't remember what our loss was before I did that, but I think it was like 0.0002 or something. Like this value is 2. But let's hope that it works better. My idea is that if we only tell the network to match one side of the object, it will be able to use all of its ability to only... Because it has to, like, when we make it symmetric, it has to, like, figure out how to copy each feature onto every side, which, like, is not a good use of its capacity. All right, please. Go, go, go. It also seems to have plateaued already, so you might be able to reduce the number of iterations here to, like, 10,000. But I like to have it run for a while because it doesn't take that much time, and I can be certain that it has hit the local minimum before it finishes. Okay, let's replace this. Okay. This is fucky, but I know why. It's because this is me mirroring the wrong side. This is me mirroring the side that's like, oh, I don't care what value you take. So I need to mirror the side that actually is the side that I want, and to do that I have to make this negative. So let's see if that works. Yeah, so now it's negative and it's symmetric and it's melty. So see this artifact down here where it's like all melty? That tends to happen when the network is overfitting, or it can also happen if you like are unlucky. Because with these small models, there's like this saying where like with a neural network, every local minimum is the same. But I think for small models, that's not totally correct. Also, it might help if I have Blender still open. It might help just to make sure that this mesh is watertight. And watertight basically just means the mesh is... Oh, this mesh is not watertight. Oh, fuck. This is screwed. Okay, so... I'm going to explain myself. So, for a mesh to be watertight, it basically means that the mesh has no holes. But I can see a hole right here. So, yeah, there's a big hole here. And also this thing doesn't actually connect with the handle. So how do we define an SDF here? Because if I have a point like right, let me see if I can place the 3D cursor. So if my point's there, right, the SDF should be 0 there, but also like we want the distance to the handle, not the distance to the wall here. So it's messed up. So we have to like do some, okay, what if I search for watertight? Okay. Watertight. So you want watertight models. That's what you should search. Watertight Utah teapot. Yeah. This should be better. Download this and save it to my downloads. Remove the .txt extension. Yeah, you're going to want to search for watertight models. Okay, so we're going to import that. Import. DAE. Downloads. Model.dae. Okay, so I'm going to already see that this is better. Yeah, so now this is better because the handle actually connects to the wall and stuff, and then there's no hole at the top. Okay, this will probably train a lot better, so let's delete this. Actually, no, let's scale this down so that it fits in the same spot. Did I delete the right one? Yes, I did. Okay. And this is, yeah, it's watertight. Okay, cool. So now we export that as our object. Export as obj. Teapot.object. Okay, so that's been exported. And then what we want to do is we want to re-import that. So let's retry. Hopefully this will work better. Okay, we're already... Oh, wow, the loss is way better now. Okay, that's probably a very good sign. Also, when we do this manual mirroring stuff, we might be able to make the model smaller. Okay, train. Faster. Yeah, that's a very low loss. So, yeah, big hint, make the model watertight. Okay, this is a good learning experience. We're learning this together. Because, like, I didn't come to this knowing how this was going to work. I had to learn all this stuff. Yeah, that's way better. Okay, so the model looks really good. And if I remove this part, actually, it's very easy for me to just, like, get hyper-focused on, like, improving things in minor ways. So, and I was about to say, stop me if that happens, but you can't stop me. This is a recording. Anyway, so here we've got our neural... Oh, yeah, we got a glitch here. See how our ray marching has stepped through the surface of the object? That can happen, especially with small features. No real way around that other than maybe reducing this value here. So this is like the bounds check. We've only defined the SDF within the unit sphere. So anything out, so if I comment this out, let's comment this thing out here. You see the abominations. So the thing about siren networks is that they're not periodic, meaning that, like, if you train a siren network in a certain domain, when you go outside of that domain, it just goes wild. So what we have to do is we have to make it so that outside of the domain that we trained, we return, like, a proxy for the distance. So probably what's happening here is that our proxy for the distance is saying, oh, you're like certain number of units away from the object, when in reality you're actually a lot closer than that. So we have to reduce this, I think. So if I change this to 0.9, yeah, the issue has gone away. So keep that in mind. This code is arbitrary. Like all things, this is arbitrary. This code's arbitrary. So you have to also fiddle with that too. My apologies that you have to really fiddle with this stuff to make it look good, but that's just the nature of this stuff. Okay. All right, so we fit this model. Let's do a little bit more experimentation. So let's try making the model smaller, because a smaller model is a happier model. Also, I forgot earlier when we were like talking about changing the precision here. Once you've like trained your model and it's all good looking and stuff, and if you want to make the model smaller, you can try reducing this to 2, and only then should you try to use it, because keep this at 3 when you're training, because otherwise it's gonna be bad. So paste this here. Okay, yeah, so oh yeah, the network did not have capacity to train this. Oh god, okay. It's so silly looking. Right. Okay, let's increase the depth, I think. Let's make it 4. I think that, like, when the number of hidden units is small, but the network is deep, you can get a lot of, like, high frequency information, like fine details and stuff like that. And when it's wide and shallow, you get, like, a really good vague shape of it, like it fits the shape pretty well, but it's very rounded. Like, it's all rounded out and stuff, but that's just my, like, hunches of how it looks. But you can see it tried to do, like, the rim of the teapot, but it couldn't quite get there, which is quite sad, really. It tried its hardest, but it couldn't succeed. Okay, loading. I am tired. I worked out yesterday for the first time in ages. I got a $20 Pilates ring, and I've been watching a Let's Play of Ring Fit Adventure, so I'm like pirating Ring Fit Adventure basically. So that's better. It's still not great. Also, people were wondering if the weird texture, like the weird bumpiness, is an artifact. It's not, it's just I thought it looked cool. So if I comment this out, if I remove this stuff here, yeah, it's not anything. It's just an effect I added because, I mean, ultimately we're making art here. Like, that's all this is art. So I wanted to make it look good. Okay, let's change this to 8. Let's see what 8 looks like. I got some strawberry milk to go to drink. I don't know if you probably haven't heard of milk to go. It's like a Canadian thing. They were like trying to turn milk into like a fitness drink. It's so weird. It's like muscle milk. Also, I love the French slogan instead of because everything in Canada it's English and French. So in English it's milk to go, but in French it's let's go, which I love. I adore that. Okay, let's run this. Oh God. Okay, so this is another scenario where like the network is overfitted. So it's like, oh, I have enough capacity now, so now I'm gonna try to like get a little bit too greedy and fit these really fine features, like fine detail features, when I can't really do that right. So maybe for these networks, it's actually better to have a wide network. So if I change this to like 24 and change it to like 1 layer, I think even though the matrix multiplies are huge, it might actually look better. I think that the skip connections work better for images and maybe not so much for the SDFs. Sorry, I'm opening up my milk. I'm opening up my let's go. Okay, copy that. Paste it over here. Paste-a-dee-doo-wah. Yeah, so that looks better, right? Like, maybe my idea of skip connections doesn't work in this domain, and sometimes you just have to admit that fact. Let's do something wild. Let's maybe make a 32-layer network with two layers. This is gonna take a while to train, but I'm not going anywhere. This is okay. When I was working on this project, I would like get up at like 7 in the morning and work nonstop and forget to eat until like 7 p.m. And that's dangerous. Don't do that. Don't be like me. Because I would just get stuck here. I'd be like, okay, that didn't work. Let me try 32 by 2. Oh, that didn't work. Let me try 32 by 3. And then just like kept going and didn't eat, which is bad. And then I got sick. But I'm better now. My milk to go is keeping me safe. Okay, cool. Huge network. Look at all that code. Okay, copy it. And we paste it over here. Paste-a-dee-doo-wah. Pasted. Oh God, that's still gonna take, yeah. So, yeah, this fits a lot better. Like, it even got the rim of the teapot. So, yeah, you gotta fiddle with this stuff a lot for it to look good. And that's just the nature of it. Like, I can't, like, there's no cookie cutter solution. Also, just for the hell of it, I'm gonna comment out that, like, this thing. So, like, yeah, so we were like, okay, only train the one side, and we'll mirror it ourselves. And this is what it looks like. This is what it looks like when you only train the one side. All right, that's about all I have. I hope this helps a little bit, and I can't wait to see what everyone does with this stuff. Bye!